Lesson 6.5, trigonometric functions. Our focus is to define the trig functions and identify single transformation. Essentially, we're looking at determining the amplitude of a trig function, determining the period of a trig function, and determining the phase shift of a trig function. So that's our main goal for today's lesson. Just a background. Now, in the previous lessons, we looked at the unit circle. So we'll be utilizing the unit circle. And remember, the unit circle, we have both degrees. We said the x-coordinate would refer to as the cos. So the cos of 30 degrees, or pi over 6 root 3 over 2. The sine of 30 degrees, or pi over 6 is a half. The tangent is 1 over root 3, which we will now, for 90 degrees, or pi over 2, we know that will be, so pi over 2 here, then show up. In this case, pi over 2 sine of pi over 2 is 1, and cos of pi over 2 is 0. Now, and the process, it repeats. The ratio repeats, except the sign will change. Remember your cast rule, only the cosine is positive in quadrant 4. All the trig functions are positive in quadrant 1. The sine is positive in quadrant 2, and the tangent is positive in quadrant 3. So using the unit circle to sketch the graph of the sine and cosine. So in your previous booklet, you did sketch the graph of the sine and cosine. Today we'll continue that. So let's review some of the work. So let's go back a little bit to, so today we're going to look at the amplitude and period of sinusoidal function of the form y equal a sine x bx, or y equal to a cos bx. Just remember, the sine and cosine functions are periodic functions. In other words, a periodic function is a function that repeats itself over a period of time. So a periodic, let's look at some definition here. So periodic function, a function that repeats itself over regular intervals or cycle. The period is the length of the interval of a domain which a graph repeats itself. And I'll show later on from our equation that the period is 2 pi over b, or 360 over b. The period is really how many cycles are there in a full circle, 360 degrees or 2 pi. So the b indicates how many cycles or periods. And the sinusoidal curve, as we say, is a name given to curves that fluctuates back and forth, like a sine graph or a cosine graph. We're also looking at the amplitude. Now the amplitude, I'll look at it here in just a moment, is half the total height of the function, or the maximum minus minimum divided by 2. And the last thing we look at is the phase shift. Is a horizontal translation. We haven't looked at the vertical translation also. That's your graph is moving up or down. So let's look at, this is what we call is a sine function, or a sinusoidal. It's a periodic, repeat itself. So the period is the distance on the x-axis of one cycle. So cycle where it starts from 0 here, goes up, goes down back, and start to repeat itself. So this would be a period. In this case, it is 2 pi, or 360 degrees. So the period is the length of this interval here, which a graph, so the graph repeats itself from here on. So this length from here to here is the period. The amplitude is the height from, we call this would be the midline. So midline, right? The midline is halfway between the maximum and the minimum. Okay, so if you look, so the midline is halfway, so we call this a midline. So halfway between the maximum, here the maximum is 1, the minimum is -1, so halfway between. So the height from the minimum to the midline is the same as the height from the midline to the maximum. So this is 1. So in this case here, we call this the amplitude. Amplitude is 1. Now the x-intercepts, they're repetition, and they're repeating every pi in this case. Okay, so this is what we call a y equals sine theta. Theta is 360 degrees, or 2 pi. So in one complete circle of 360 degrees, just have one cycle. Okay. We'll talk about the phase shift. The phase shift refers to the horizontal translation. Generally, a sine graph begins at origin 0, 0. But if it shifts from, let's say, pi over 2, then the phase shift would be pi over 2. We'll look at that later on. So a general sine function, and you've done it before, this is from your booklet. This is a characteristic of a sine function. And if you were to look at your, it's all derived from your unit circle. So sine of 0 is 0. Sine of 90 degrees, or pi over 2, is 1. So here we go, like sine of 0 is 0. Sine of 90 degrees is 1. Sine of 180 degrees, or pi, is 0. Okay. 3 over 2 pi, what is sine? Sine is -1. So these are your main points. Now we're back to 2 pi. So sine of 2 pi is 0. Okay. And we fill, and these fulfill our, so we have 0, 0 here, sine of 0. Pi over 2 is 90. And it's all from your unit circle. Now you can complete, you can go ahead and fill in the other section here, like say pi over 4, or pi over 3, or pi over 6, and you find the y values. So the y-intercept, let's go back for this graph here. Now, the period here is from, as I mentioned, the period is the length of the interval, right, where the graph repeats itself. So the length of this interval here to here, is 2 pi. So we can say the period here is 2 pi because it's the length of the interval. So we can say here is the length of the interval of the domain. So this is your domain here, over which a graph repeats itself. So the graph will repeat. And if this were to continue, as I'll show you this previous one here, this graph repeats itself. Or you can go to the left, right? It's repeating. So every 2 pi is a complete cycle. Okay, so you can repeat itself every 2 pi. In this case, we'll show you it varies. The y-intercept, notice here, there's only one y-intercept here. So it's only one, which is 0, 0, right? So only one y-intercept. And we're looking at one cycle. Then looking at more than one, just looking at one cycle. Even if you were to go beyond one cycle, as you can see here, there's only one y-intercept for a y equal sine x graph. Now the x-intercept in this one cycle would be 0, pi, and 2 pi. So it would be 0, pi, and 2 pi. These are the x-intercepts. The domain, we're looking at, this is one cycle here, right? Domain. And this giving you here, right? It's from 0 to 2 pi. We restricted at this domain here. The domain is from x is between 2 pi and 0. Now, the range is from -1 to +1. So, -1 and includes 1. The amplitude is from the midline, which is y is equal to 0. And the midline, the equation is always y equal to where the line that's middle between the maximum and minimum values of the sinusoidal function. So the amplitude here is 1. So this is your amplitude here. So make this. So amplitude equal 1. The maximum value is the maximum point where the graph extends. So we say it's 1. The minimum value is -1. So that's the graph of a sine, general sine function. Now let's look at the graph that's on the next page of your booklet. And this would be your cosine. And they're restricted between 0 and 2 pi. And this again, you probably want to refer back to your unit circle. Right? And I try to, maybe this doesn't look so clear. I'm trying to find one. Just zoom out here. So let's find 5 key points. We have x equals 0, so we have 0 here. Y is 1. Pi over 2 is 0. Pi is -1. And 3 pi over 2 is 0. And 2 pi is equal to 1. Now, where do we get this from? And it's from our unit circle. Remember, we're dealing with cos. The cos. Now, cos of 0 degrees is 1. So we got that one. Cos of 0 degrees is 1. Cos of pi over 2 is 0. Cos of pi is -1. Okay. Cos of 3 pi over 2 is 0. Because remember, it's the x-coordinate of your terminal point on the unit circle. Then go back all the way here 2 pi, it's 1. So that's why we end up with a using a unit circle as standard. Remember, this x refers to 2 pi. So we're looking at, and there's a 1 in front there. Tells me we know that what the 1 means the amplitude. So the x by definition is 2 pi or 360 degrees. So here, in this case here, we say there's one period in a complete cycle of 360 degrees or 2 pi. So let's look at the x and y-intercept. There's only one. X-intercept, x is 0, y is 1. Sorry, y-intercept is 1. The x-intercept now, we have them at pi over 2, and we have a 3 pi over 2. And we know that from here, right? We have pi over 2 cos is 0, and 3 pi over 2 cos is 0. The domain, we're given a restricted domain here. It's from 0 to 2 pi. Or if you're working in degrees, it will be 360 degrees. The range now is from -1 to 1. The amplitude again would be your, now this is our midline and this is our amplitude. Doesn't matter, that's my amplitude. This is your amplitude here. This is your midline. Y equals 0. Now the midline will change depending on the function given, but this is what you call your base graph. Looking at a circle of one cycle, this is what your graph will look like. We'll look at transformation later on. The amplitude is 1. The period here goes from the period now, which is distance of the horizontal distance here. So the period is from here to there, which is 2 pi. Maximum value is 1. Minimum value is -1. So that's your general y equals sine x, y equal cos x graph, and we did the previous one, y equal to sine x graph. So today we are going to look at graphs where we find the amplitude. So let's define what these mean. So now the amplitude is have a total height of the function, the vertical stretch or compression. So we're looking at compression, right? We're looking at the value of, in this case, we're looking at A, the value in front of the cos or the sine. So the amplitude is normally the maximum. So if you can write here, the amplitude is your maximum value minus your minimum divided by 2. So if I have my maximum, so here in this case, I have 1 minus 1 over 2, which is 1 plus 1 over 2, which is equal to 2 over 2, which is 1. That's the algebraic way of finding it. But if you're given a sketch, you can find the midline, or you find the maximum minus the minimum. Or from your equation, the A value here later on will show you, right, what that A means. Okay. So that's your, now the midline, which is critical, is halfway between the maximum and the minimum. So essentially, so the midline, if you want to find the midline algebraically, is your maximum plus your minimum divided by, it's like your average, right? So in this case here, we have our maximum is 1 minus our minimum, or plus minus 1 over 2, which is 0 over 2 is equal to 0. So that's why we can say y is equal to 0 for your midline. Now the period, you can do it visually. You find the period now is from a maximum to a maximum here. So one maximum to another maximum to the length of the horizontal axis. Or if you go back to your sine function now, it's where it begins and where it ends. That's the length of the period. Now, unless they give you a restriction, the domain is all the real numbers, right? In this case here, the arrowhead continues, so the domain would be all the real numbers. There's no restriction here. The period, though, is still the same. You can go from maximum here to maximum. And you have the same measurement. The midline, it's your maximum plus your minimum divided by 2, and the amplitude is from your midline to the maximum or midline to the minimum. So the vertical translation, we'll look at that later. But for now, we're looking at sketching your sine or cosine function. Now, I'm just going to show you the illustration of what I did earlier. Here we have our unit circle, and if you were to translate it, you get back all the points. That's how we look at a cycle. And that's for a sine, and the cos would be the same thing. In previous lesson, we looked at sketching the sine function. And if you look at the sketching, look at the details, if I were to pick all of the points on the coordinate on the unit circle, if I look at all of the points here for sine, and I'm more detailed, you end up with a cycle. This is in degrees and this is in radians. So these are the characteristics we looked at earlier. The curve is periodic. The curve is continuous because it is continuing, it's a cycle. The range is from -1 to 1 because we're looking at the unit circle of radius 1. So here is -1 to 1. The maximum value is +1, the minimum value is 1, the amplitude of the curve is 1. So it's your amplitude here or here. So 1 to 0, so midline. The period is 360 degrees or 2 pi, and the y-intercept is 0. Notice there's only one y-intercept. And we said the maximum vertical distance of the graph above the horizontal central axis above the curve. So that's the midline here. So let's look at a couple of questions, and then we'll look at the ones from your textbook. So determine the amplitude of a sine function. So any function of the form y equal to a of x is related to y is equal to f of x by a vertical stretch factor of a. So the value in front, the a value, is your amplitude. So if you have a stretch or a compression based on the a value, if the a is less than between 0 and 1, you have a compression. If the a is greater than 1, you have a stretch. If it's negative, you have a reflection. Same as what you did earlier in transformation. Okay, so so let's look at this one here. A equals okay, this from my, let me look for a graph. Okay, here's my graph paper. So I'll use some graph paper here to graph this function. So let me make sure I can zoom out a little bit here so you can see the question. We'll use a method of graphing, and then I'll show you the one using the algebraic one, where you find the amplitude. So we have the first one on the same set of axes, graph y equal to 3 sine x, y equal to 0.5x, and negative 2x for between 0 and 2 pi. So I already have a template here. I don't really need this negative here, but I'm going from 0 to 2 pi. And I'm going to graph each one of these on the same graph, put A. Then we're going to state the amplitude for each function and complete each graph with the y of sine of x. So first of all, we want to construct y of sine of x. Now, in the previous one, and it's in your booklet, we know what the graph of sine of x looks like. Okay, so let's. So if we go back to our y of sine of x, which is this one here. So we'll have here. So this is going to be 1, negative 1, 2, 3, negative 2, negative 3, negative 4. Up to 4. So have a complete cycle here. So remember x. Now when you're sketching a sine function, you're looking at 4 parts to it, and it's like a replication of your in a circle. We start from 0, pi over 2, pi, 3 over 2 pi, and 2 pi. So those are the 4 critical points you're looking at. Pi over 2. So you have 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we can add more in between, but this is 4 you need, 4 points you need. So x is 0. And I'm going to go back to I'm referring to this here. So x is 0, y is 0, pi over 2 is 1. Sine, I'm looking at sine here, y equal sine x. Remember, x is 360 degrees, or 2 pi. Next one is negative 1 and 0. So this is my y equal to sine x graph. So y equal to sine x. Looks kind of flat because the amplitude is 1. So that's right. Now, the next thing you want to do is to graph y equal to 3 sine x. Now, notice, right, y equals sine x, that here, it's 1 amplitude. Now, now we have a stretch of 3. It's exactly this thing now. Instead of it now, this goes from 1, it goes to 3. So we go up there 3 units. So I'm going to go down. And now we're going to go down here to negative 3. So now I'm going to use, this is my, so y is equal to 3 sine x. Let me just sketch. Not perfectly symmetrical, but you get the picture here. Now the next one is half. Notice now it's going to be half of the normal sine graph. So now it's somewhere around here. So maybe I'll use maybe use a pen. So here we have half. Go back here. So now, we have now negative 2. Now, just imagine, right? The reverse is a reflection. So negative 2 is a reflection. So now we're going down Because remember, this is your point here, -2. So we have a reflection here, -2, go up here, and +2. So there are our three. Since our amplitude, and know this right, my amplitude here is 3 for the first one. Amplitude here is 2, notice, and this is a good indication that's the value of your amplitude. So the first one is 3, next one is 2, even though it's a reflection. Remember, the amplitude is from your midline to the maximum, and the next one is the amplitude is a half. Now y equals sine x is 1 in front, so the amplitude is 1. So the first one we have for A, we can then write this down. So for A, so using the graphing method, right? So for A, we have here, so we have y. So we first of all, step 1, let's do this first here. So step 1, sketch the graph of y is equal to sine x. That's what we did here. Y is equal to sine x. We sketch the graph first. Now, once we sketch a graph, then we sketch the other graphs, right? Y equal to, and by looking at the stretch. So for y equals 3 sine x, you have a vertical stretch by a factor of 3, and that's here. So y is equal to 0.5 sine x. This is a vertical compression. Of 0.5, and y is equal to -2 sine x. We have a reflection in the x-axis and a vertical stretch by a factor of 2. So that's our one using the graph. Okay. Now, what happens when determine the amplitude of each function? Now, the amplitude of each function, we can use a formula. Let's look at your so B in amplitude. Amplitude is equal to the maximum value minus your minimum value divided by 2. So for the first one, so for y is equal to 3 sine x. Now I can tell right away from the value here is 3, but if you look back at our graph, right here, our maximum is 3, our minimum is -3. So our maximum 3, minimum -3. So we have 3 minus 3 over 2, which is 6. Oops. 6 over 2 is 3. So the amplitude for the first one, right, is 3. Right. For y equals 0.5 sine x, go back to the here, is from 0.5 to 0.5, right? So maximum 0.5 or 0.5, and minimum is -0.5. So here we have 0.5 minus over 2, which gives us 0.5. And the last one here is y is equal to -2 sine x. And you go back to our graph, we have -2, 2. So what we have here, we have 2 minus 2 over 2, which gives us 2. So max is equal to 2, minimum is -2. So in the last part, compare each graph of the function sine x, consider the period, amplitude, domain, and range. And if we were to look at them, right, so the period is all the same. Period is 1, right, because from 0 to 2 pi. The range, it varies, okay, depending on the amplitude. So for the 3 sine x, it's from -3 to 3 is your range. For -2.5 is 2.5 to 2.5, and 0.5 is from -0.5 to +0.5. So the range changes the amplitude, so we can include the amplitude. So if you look at this graph, any kind of function, the a value gives us your amplitude. If it's negative, we know it's a reflection. And many times you're given a restricted domain. Just finding your sine function. So let's look at one from your textbook here. You're given. Here we have cosine. Now I already have the standard cosine function. And you're asked to determine the amplitude and graph of each function. So we know right away the amplitude is 3. So we have a stretch. So this is your standard 1 cos. So now we're going to stretch this guy to 3. And to be -3. So these are my points here. 3. So from our graph, right, it's been vertically stretched. So we have a vertical stretch. By a factor of 3. For the original one, we have the amplitude is 1, so the amplitude is equal to 3. So the amplitude equals 3. Now here we have our sine function, but we have a reflection of a half. So now we have a half, but it's a reflection. So we have a half here. So half, so a point here. So notice it's flatter, right? So we have a vertical compression of, sorry, a half. And not only that, right, it's reflected, right? It's reflection. So we say the amplitude is equal to a half. Okay, so let's go to the next one here. Next part, we're looking at period of a trig function. So before I go to this, there's some notes on that. Now the period of y equals sine b of x or y equals cos of x, right? Now the period, as we mentioned at the beginning, it's the length of the interval of a domain over which the graph repeats itself. So if the graph is repeating, we're looking at the length of that. So in other words, how many repetitions do we have within 2 pi, right? So the length of this here. So if there's there's just one repetition here, we know the period is 1, but the length of the period would be 2 pi. So it may vary. Now, the other part of it is, once you have the equation, the b of that 2 pi over b would be our period, but we haven't reached there yet. So we're looking at the horizontal length of one cycle. This horizontal length in one cycle. That's the period. So to determine the period, so this shows you the remainder, that the absolute value b, right? Will give you the period in the graph. So the b value here, so this is your a, so we have y is equal to a sine b of x. Now the a, oops, you didn't see that here. So the a is your amplitude. The b will give you the period, right? But the period, where b is not equal to 0, so the b will tell you your 2 pi over the b will give you the period. I'll explain to you why that means. The b refers to how many cycles, right? Or how many periods are there in one complete circle. That's why we divide by the b, whatever the b value is, 2 pi or 360 divided by the b value will give you the period. So we're looking at, for example, so we'll look at how do we find one, right? So begin with the interval of one cycle, sine x or sine cos of x, and replace x with b of x for the interval of one cycle, and divide by b. So 2 pi over b, or 360 divided by b, give you the period. Okay. So let's look at an example right now. Now we'll go to it. So this is our question. So here's our question. So any function of the form y f of x related to y f of x, so it's a horizontal stretch. So we're looking at the horizontal stretch of 1 over absolute value of b. Right? So here we give a sketchy graph of the function y equal to sine 4x between x 360 and 0. And so we'll look at that in here. And we're going to sketch a function where it's half of x. So we have two of these. So first of all, I need to get a graph paper and so here I have a standard y equals sine of x graph. Okay. So that's, now we want a graph that's y is equal to sine 4x. Algebraically, the period here would be 2 pi over 4, or 360 over 4. Since we're dealing with the radians here, we'll stick with the radians. So in other words, the period here now is half a pi, right? 1 over 2 is half a pi. So half a pi is the period. Rather than this period here is 2 pi, it's half a pi. Okay. In other words, we'll have a horizontal stretch of a quarter. So the stretch now, so we have a horizontal stretch of 1, it's 1 over b. So now this is your b value. So it's 1 over 4. So we have a horizontal stretch by a factor of a quarter. Okay. So here we have, but also the period is half a pi. So now instead of it being complete here, the period ends there. Now the question is, here I have a sine, oh, this is 2, value 2, sorry, this one here, the sine, this y is equal to 2 sine x, 1x will be there. So this is sine x. And this is sine 2x. But now I want to sketch y is equal to 4. So y is equal to sine 4x. We already established that is a horizontal stretch, or it's actually a horizontal compression, right? Horizontal stretch of a quarter. We said more or less a horizontal compression, not a stretch. Compression of a quarter. Okay. So now the period is a quarter, or a half, sorry. So it's compressing by a quarter, or the period is a half. So now we have, here are our points, our critical points going to be a quarter. So graph ends here. So we start here. So this is, of course, now it's a half of what it was. So we have a half here. Okay, the amplitude is 1. So that's your sine 4x graph, the amplitude. 1. So the period there is 2 pi. So let's look at an example from your textbook. So here in your textbook, we have so determine the period of each function. We can look at here, we can say the period here is 2 pi over b. This is your b. So y is equal to a sine b of x. So b is equal to 2. So the period, oops, there we go. Sorry about that. Period is 2 pi over b. It's given here. So now we have, so the period is equal to 2 pi over 2, which is equal to 1 pi. So this is our general sine graph. Y is equal to sine x. But now we have a compression now. So if we're looking at b is 1 over absolute value of b, so it's 1 over, this case is 2. We have a compression of a half, horizontal compression of a half. But the period here now we know is AOD here is 1 pi. So now we have circum here, it goes up here, down there. So as I mentioned before, you're looking at the 4 main points and quarters. Try to think of each cycle divided into 4 parts. So no matter which one you use, right, you always think of it as divided into 4. It's much easier to divide it into 4 because you have your maximum, your minimum, and your midline. Now, the next few lessons, 2 lessons from now, we're looking at the vertical shift and the horizontal shift. So that's your first one, first graph. So the period here, so we see the period, so period is equal to 2 pi is equal to pi. So the period of y with the 2 sine x is equal to pi. So we have a compression of half, right? But a period of 1. Now cos of x. Now remember our cos of x graph, what it will look like. I'm just going to put 1 up here and make it look a bit compact. So remember cos graph starts from here, goes there, down. So cycle. Oh, you've seen it there. Okay, sorry about that. And come up and back up here. This is my cos. Y is equal to cos of x. So remember, this is 1. The amplitude is 1. The period is, remember, this is 2 pi. And 1 is the amplitude. The question is, you want to find the period for y is equal to 3/4. Oh, no, sorry. Y is equal to cos 3/4 x. Now the amplitude is 1. Now it's the image of this graph here we're looking at, right? But we have a horizontal factor of 1 over, so the stretch, right? Horizontal stretch. So the horizontal stretch and this will be a stretch in this case, TCH, which is equal to 1, so that 1 over b, which is 1 over 3/4, which is equal to 4/3. So we have a horizontal stretch of 4 or 1 1/3. So that's your horizontal stretch. Now the period, so the period for this now is equal to 2 pi over b. Which will give us 2 pi divided by 3/4, which is equal to, what will that be equal to? 8 over 3 pi, or 2 2/3 pi. So the period is quite not neatly done. It's a pretty messy one. So the period is equal to 2 2/3. So if you were to sketch that now, I need to extend this graph a bit further. So this graph is actually 2 2/3 over here. So the graph is really stretched. The amplitude is still the same, except the graph is stretched away in 2 2/3 pi. So it will be way on the other side over here. The graph will stretch to 2 2/3 pi. So if you were to, so you have 2 pi here. Extend this graph a little bit more here. We have 1 pi, so 2.5 pi. Now we have 2/3, and we have 2 3/4 pi, or so 2 2/3 would be here. So for each one of these, so we're looking at a point here, approximately. So our graph will actually be stretched out and ends up here, up here. If you were to sketch that graph. We didn't ask us to sketch it, but just want to show you if you were to sketch that graph now. So now, if you want to sketch this now, you go to your period here and divide it into 4 parts. So 8 over 3 divided by 4, or multiplied by 1 over 4, which, so each section, so we want to know each part of it, will give us what? 2/3. 2/3 pi will be each part. So we have, here we have, so 2/3 pi will be somewhere close to here. So next we have another 2/3 pi, which would be close to there. Okay. So we have 1. And here we have 2/3 pi, be somewhere down here. And finally, we have our 2/3 pi up here. So now our graph, what looks like, and we'll start from here. Oops, no, we start from 0 here. Look at that. So you can see it's a stretch. That sort of a messy graph. So all I want you to know for now, for this question asking find the period, and the period is 2 pi over b, which is 2 2/3 or 8 over 3 pi. The last thing we'll cover today is your phase shift. Now the phase shift, you're looking at a horizontal shift of the graph. And in this case, we're looking at a tangent, right? And here you sketch a phase shift of a tangency, right? Now, we wouldn't focus much on tangent, but I'll look at one where it's cos, okay? Because we got tangent, we'll skip this one here and we look at the cos because a tangent graph is not a sinusoidal one. But we'll look at that one. But let's look at phase shift. But basically, we're looking at when you have a function of this sort now so far we look at y is equal to a sine b x. Now, what we're having now, we're having a horizontal shift now. Instead of a graph beginning at, say, a 0 here, it may be beginning at a different point on the x. So your graph will look like minus c here. So this is your amplitude. This we just did is a phase shift. Sorry, not phase shift, or horizontal compression or stretch. This is 1 over b. Now, the c now is a phase shift. So it's basically a horizontal translation. So C is a horizontal translation. So we'll use that fact that horizontal translation refers to the phase shift. So in general, the graph of y equal to sine x minus c is the image after the graph has been translated to c and it's horizontally. If it's negative, it shifts to the right. If it's positive, it shifts, c is positive, shift to the left. And that's referred to as a phase shift of the function. So I want to look at this one here, determine the phase shift of the function y equal to cos x minus pi over 2. Now, look at this graph here. If you look at a cos graph, right? So let's look at 1, -1. So here is my, oops, I'm looking at cos here. So here's my points here for cos. Now, this is, if you were to write it out, is y is equal to 1 cos 1 x minus 0. There's no horizontal shift here, so no phase shift. But if you look at this here, the phase shift now is going to be pi over 6 units to the right. So the phase shift here is pi over 6 to the right. So instead of this graph now starting from 0 here, the y-intercept is 0, it's now shift pi over 6. So we know this is going to be pi over 4. So pi over 6 would be somewhere here. So it's actually shifting to the right. So you graph, everything shifts now to the right. pi over 6. The graph would be, oops, then, oops, and pi over 6. So this is a sketch of the shift of the graph. It's shifting pi over 6 units to the right. Now, if you were to do a sine function, let's do a different one. And even though it said cos there, it's a repetition. I'm going to move this here. And let's say, let's do 1 phase where we have a y is equal to sine x minus pi. Okay, now this is my regular, do a regular sine graph. So we have 0, working out the full graph. Now, if it shifts negative pi, pi units, and now it's now instead of starting from 0 here, it's now, I'll use a pencil. So now here are my points. My point's going to be now starting from here, and you're going to go up here, down here. So that's my graph. Come up down here. Now it's going to go, and I have to extend it now to pi. So this is 2.5 pi, which is 2.5 pi. So this is a horizontal shift. We call it a phase shift. So a phase shift, oops, of pi units. Now, if this was positive, then it will be starting from here instead. So so here we have y is equal to sine x plus pi. So we start from negative pi here. So we still have the period is still x here, right? Which we haven't shifted it. We haven't changed the phase here. We haven't changed the compression. It's still the same as one cycle. Sine of x here. There's no b. Sorry, it's a b, but the b is 1, which is 2 pi as your period. So we start from here. 1, 2, 3, 4. So we start from here, goes up, comes down, and that's your cycle. So this here is y is equal to sine x plus pi. Okay, so that's it for today. Your assignment questions are to look at your textbook. So your assignment, you want to try on page or assignment. So page 521, question 3, and question 4. The next lesson, I'll be going over some of the questions and looking at transformation of sinusoidal function, extending it to horizontal vertical shift. So far, today we looked at the amplitude, the period, and the phase shift. The next lesson we'll be looking at vertical shift, which is the final part. So far we've looked, the equation would be y is equal to a sine b into x minus c. So that's for today, right? Or y is equal to a cos b into x minus c. And we said that a is equal to the amplitude, b is equal to the horizontal compression, or stretch, c is the phase shift, or horizontal translation. The next thing we'll add here is a vertical translation, which we haven't had it yet. So tomorrow we'll be looking at, or the next class, y is equal to a sine b into x minus c plus d. And the d in this case is your vertical translation. So we can look at different forms of transformation.